Well, welcome back to my channel. In today's video, I've got something interesting to show you. Let's take a look. Here we go. Sigma Comparator. Let me know in the comments section if you've ever seen one of these before. Bring you closer. So this Sigma Comparator is a 500 nanometer per division instrument. And as you can see, you've got both metric and imperial scales. The measuring needle. Also, with this particular Sigma model, there is a mirror strip in the background. And this is to help you prevent parallax error when taking your readings. And what these are to set your parameters. So you set your tolerances up on your scale, and you generally set these up with these work in conjunction with gauge blocks. So you need a known calibrated size of a gauge block, and what I tend to do is I set the bottom parameter with a known calibrated size gauge block for the bottom limit of whatever the product tolerance is, and the top parameter for the top limit tolerance range, also with another gauge block of a known calibrated size. And effectively all the comparator does is just indicate your readings. They're very easy to use. And as I said, they work with gauge blocks. So always have a set of gauge blocks with this when using it. I just want to say, Sigma Instruments is an old English company that no longer exists, and nothing to do with any modern namesakes. Sigma comparators were actually very popular in the 1940s and 1950s. So this is my 1 micron per division Sigma comparator. So I'm just setting up a 30mm gauge block. And I can rotate the thimble and the back here in order to adjust the pointer, of course, to my known calibrated size gauge block. So I set the 30mm to 0. So that's 29.995mm, this gauge block size. 5 microns less than the 30mm gauge block, which I set to 0. As you can see, you've got 1 microns per division on the metric side of the scale. And on the right hand side, you've got your imperial scale readings. And of course, I can set my parameter. So if I'm working to a tolerance of 30mm plus or minus 5 microns, then of course you set the instrument to your known calibrated gauge block sizes, one for your bottom limit and one for your top limit. So that's 29.995. Put the 30mm back on. Should be straight back to the 0 reading, as it is. Yes, it's nice to have a big screen. At least it's nice and visible. The most magnified Sigma comparator that I've come across to is the 500 nanometer per division. Although I have heard from various old books that there has been a 100 nanometer per division Sigma comparator, but I've never seen one. Let me know in the comments section if anyone has actually come across to a Sigma comparator that reads down to 100 nanometers per division, or even more magnified than that, I would be interested to know. And this is what one looks like with the cover off. It's an entirely different mechanism to the Mikrokator. The Mikrokator is based on a twisted band which partially unwinds and rotates when stretched, and it's attached via a cantilever and a flexure spring, which in turn is connected to the plunger. So this system is based on a forked arm, which is just behind the dial plate, and the forked arm is attached to a crossed strip hinge, which has a sapphire crystal bearing block. I'll bring the camera a little bit closer, but this is the cross strip hinge, and there's a sapphire bearing block on the top here with this pivot point, which is in turn is attached to the plunger via these flexure springs, is pivoting on the sapphire crystal bearing block. It is this that actually allows you to calibrate the mechanism with, of course, with known calibrated size gauge blocks. And on the opposite side, so the other end of the forked arm is attached to the aluminium damping disc, which in turn connects to the pointing needle, and it's tied up together. So the forked arm has two prongs which are actually attached together with a phosphorus bronze wrapped in between a little piston which turns the aluminium disc. So what happens is when the needle moves up and down, the aluminium disc rotates, and as it rotates, the magnet right next to it induces eddy currents into the disc, which in turn create their own electromagnetic field, and it repels against the magnetic field generated by the magnet. Effectively, it's Lenz's law, and that's a dampening motion. This is what causes the dampening motion here. So I just brought it closer up. So you're looking at the horseshoe magnet with the aluminium disc attached to the measuring needle, and the forked arm is attached to a little shaft. You can see, just about see it right in the middle, which in turn is wrapped by a phosphorus bronze band. So effectively the forked arm attached to the moving member of the hinge, which is on the opposite side, effectively transmits rotary motion to the indicator driving the drum. And this drum is through a bronze band wrapped round the drum. And as I said, this is where the dampening motion is caused by the magnet. Effectively, the dampening motion is Lenz's law. You can just about see it rotate. So that's what causes the dampening motion. And that's what the magnet's there for. And this is the opposite side. And what you're looking at here is the knife edge. Effectively, the knife edge is fixed to the side of the bar, which, as you can see, which sits on the sapphire bearing block. So this is the sapphire bearing block just inside there. So the knife edge, as you can see, is sitting on the sapphire bearing block, which in turn is on the cross strip hinge, which of course, as you can see, is attached to the moving member. There you go. As mentioned earlier, when you recalibrate these, you adjust the knife edge. The hinge is pre-tensioned to allow it to rotate within the range of the instrument scale. Anyway, I'm going to show you the fine adjustment thimble. So the whole head can be removed, and you can interchange it with another Sigma head. And behind the Sigma comparator head is a casting with a set of flexure springs, and this thimble here rotates and allows you to adjust the height in fine increments onto your specimen, and that's what this does here. So effectively all this does is, via the flexure springs behind, just allows you to adjust the head up and down in fine increments by applying, obviously when it's applied with pressure over a specimen on top of the anvil, then you will notice the needle going up, but you won't notice anything at the moment because it's a separate unit. Now I've got another Sigma Comparator head which needs repairing. So what I'm going to do is I'm going to, because I've only got 2 major Sigma Comparator stands, and what I will do is take this head off and interchange it with the other Sigma head that needs repairing onto this stand, and then we'll open it up and see what's wrong with it. The most common failure that I've come across to with the Sigma comparators is a broken phos-bronze band. The phosphorus-bronze band which I showed you on the opposite side, because they're quite delicate, they're very thin, and they tend to be the first things that break, and it's generally caused by mishandling. So it's either mishandling in use or during transportation. Unfortunately, a lot of people throw these away, which is a shame really, because they're such wonderful instruments. But no, a lot of people just throw them away and break them up, which is quite heartbreaking really. Even though they are robust and rigid and excellent for use in the precision grinding toolroom departments, you still need to take care when using them. After all, there is a lot of mechanical components inside. It's virtually like clockwork. Anyway, I'm going to put the cover back on. Just to let you know, this phos-bronze band for this 1 micron per division Sigma was one that I made myself, as the previous one had snapped when I first bought it. And I made this from a sheet of phos-bronze that I purchased from a model railway shop. If anyone's seen these Sigma comparators in their basement or shed or anywhere, please don't throw them away. If you can, find someone who will have them so they can give them a nice home. Because these instruments they're extremely reliable, they're very robust, and they are very, very useful. If you can, find someone who will appreciate them and give them a nice home, because these are, in my opinion, very valuable, and they're extremely useful. And as I said, there's been many cases throughout my career in various industries I've worked in, and we've always kept these comparators because they've just proven to be so reliable. And yeah, so please don't throw them away, save them, find someone who will take them in. Anyway, this Sigma comparator head seeks medical attention, so what I'm going to do is get my put my overalls on, my gloves on, and I'll bring you closer up and we'll open one up. Okay, well this is the Sigma comparator that we need to figure out what's actually wrong with it. And first of all, I'm going to open the front cover. It's the inside of the cover. Parameters. And as you can see, the needle is just stuck at the top. Well, it is partly spring-loaded, but there's no movement for it to come down, because by right it should come down to the bottom. I will mention these comparators can only work in this in this upright position. If you turn these on their side, you won't be able to use them, not like a normal dial test indicator or even a Mikrokator. They can only be used in this upright position. So effectively they are pretty much bound by gravity. Unfortunately, I can't get the stylus off. It's really locked in there solid. I'll have to see what I can do with that, about that a little bit later. But for now, I'll just get the cover off and let's just have a look and see, what's inside. Yeah. I can see one problem. I mentioned earlier that the most common failures is a broken phos-bronze band, and we have exactly just that. I want to see if you can see if I can zoom in. It's a brass dial plate. And this is the fork arm I was talking about earlier. So this is the fork arm. Well, I call it the fork arm. The Y arm, which is effectively connected between the crossed hinge and the little spindle just inside there, which is attached to an aluminium disc. This is the aluminium disc here, and between the two ends of the Y arm is wrapped via the little spindle with a phos-bronze band, which is broken. And the movement of this in turn rotates the needle. It's quite nice and clean inside, to be absolutely honest with you. Anyway, I'm going to carefully remove the magnet and then we'll take a closer look. It's the magnet. That's the phos-bronze band. And this is the reason why the needle doesn't come back down. Right, first thing I'm going to do is remove the phosphorus bronze. I'm going to measure this phosphorus bronze band up, take it off. First of all, I'm going to remove this from here, measure it up, and I'm going to make a new phosphorus bronze band from scratch. So I should have a sheet of phos bronze. As I said earlier, I normally get hold of them from the model railroad shops. But first of all, let me get this off, and then we'll measure it up. And I'll have to take my gloves off because I can't get enough feel when I remove this because it's very, very small. Okay, and that's now removed. So that's now decoupled from the Y arm. Now I'm going to take this off so I can get the spindle off here. and then I can take the phos-bronze off the spindle. So first of all, I'm just going to take the spindle out of here. And that's the phos-bronze band. So I'm going to measure this up, find out what the thickness is, and then we're going to make one from scratch, from a sheet of phos-bronze. Right, measuring along the length, it appears as though this broken band measures 0.03 to 0.05 millimeters in thickness, and that's pretty much the same as the other one I repaired, so I'm assuming that must be the original thickness. Oh, I'm not sure if I did mention earlier, this Sigma comparator is a 2 micron per division comparator. I will mention both of my main block anvils on both comparator stands do need relapping. So that is also something I'll be doing going forward. First of all, I'll make a new bronze strip for this Sigma. Check it over, tune it in, and then relap both of the main anvil blocks. I have got two large lapping plates which I need to dig out. But unfortunately they do need resurfacing because they're quite worn. So first of all, yeah, so after I've done the phosphorus bronze band, then after that we'll dig out the lapping plates, we'll resurface the lapping plates on camera together. After we've done the after we've made the phosphorus bronze band, which you'll see going forward, we'll dig out the lapping plates, resurface the lapping plates. That'll be another task to do, and then we can go on and lap the anvils. So there's plenty to do. So yeah, so going forward, this is part 1. So next week will be part 2. And we'll be making the new phosphorus bronze band, and then after that we'll have a look at the lapping plates, and then we'll be resurfacing the lapping plates. Unfortunately, I don't have a surface grinder, and I don't know anyone near me who does. So with these large lapping plates that I've got, re-scraping them. So I'll be scraping all the high points off to get them as flat as I can, and then lap them together. But anyway, we'll come to that when we after we've done this band, this bronze strip band. Well, that's it, everyone. I hope you enjoyed today's video. If you did, hit that like button. Don't forget to subscribe to my channel, and by all means do leave a comment. I would be interested to know if anyone's ever come across to a Sigma comparator before, and if so, what's the most magnified Sigma comparator you've ever come across to. I'll be interested to know. As I said, the most magnified one I've ever used is a 500 nanometer per division. So going forward, as I said, I'm going to carry on measuring up that phos-bronze strip. So we'll do this for next week, and we'll be making a new strip from scratch. I've got to measure the length as well. Oh, and the width. I need to measure the width as well of the phos-bronze. So I'll do that on the using the SIP. I'll do that using the scopes on the SIP universal measuring machine, and then I'll set up a template. I have got some phos-bronze actually. There's a bit of the phos-bronze sheet which I picked up from the model railway shop. Unfortunately, the phosphorus bronze sheet measures 0.1 millimeters thick. There's 100 microns in thickness. So I'll have to rub it down to get down to the required thickness based on the thickness that I measured of what came out of that Sigma comparator. So we'll do that for the next video, and then I need to relap the main anvils as well for both Sigma comparator stands. So I've got two large lapping plates which I need to dig up, but they do need resurfacing. So we'll do that as well after we've made the new strip. So there's plenty to go through, and I look forward to seeing you next week, which will be part 2. Until then, take care, and I'll see you then. Goodbye.